Welcome back. So, let me remind you that we were discussing in the last class the vibratory ball feeder and different effects. So, we have seen that first effect is that F into Vm remains constant. This is a theoretical work, and because of that we said this the if we have to increase the conveying velocity. So, the frequency to be selected as low as possible, that means the amplitude of vibration has to be more, has to be as much as possible. Second one which we have discussed is the effect of track acceleration, and we said that beyond an by gn value of some 1.72, the impact velocity becomes very high, and then the conveying velocity therefore becomes not increasing as much as it is for n by gn value less than 1.7 or 2. So, first thing is that n by gn, which is the normal track acceleration, it has to be more than 1 for the parts to hop. So, it is hopping, and as n by gn is increasing more and more, the hopping amplitude will be more, and therefore, the impact velocity will be more, and while landing on the track the part becomes unstable, and therefore, the conveying velocity decreases. That is another thing that we have discussed in the last class. Effect of vibration angle, we said there is an existence of an optimum vibration angle for different values of mu s, that is a static coefficient of friction, and as we are increasing the vibration angle, the F into Vm increases, all right, but it becomes stable after some time, and then it decreases because of the same effect as we have seen in the case of track acceleration. We have discussed the effect of track angle, and we said that there is a very strange phenomena that when the track angle is 0, the F into Vm, which is the conveying velocity, that is maximum. So, therefore, the parts located at the bottom of the ball feeder, they will push the parts which are located above where the track angle is more than 0. That is another conclusion. Next, what we said is the effect of coefficient of friction. So, we said that coefficient of friction more, that means your conveying velocity of the ball feeder will be more. So, therefore, there is a point in coating the track with rubber, so that the coefficient of friction, rubber or some material, so that the coefficient of friction could be more. But however, as we said last time, discussed last time, that it has to be decided based on the combination of the material of the track and the part that is being conveyed. So, this much we have seen last time. Let us see some numerical example through which we can find out that how these the theory that we have discussed that can be applied. Let us say problem 1. So, we will come to the first example of the flow line performance which we have discussed earlier, and let us take an example of the flow line performance. For example, a machine tool component has to be produced on a 10 station transfer machine. The ideal cycle time of which is 1 minute, Tc, I will remind you, which we have done 2 classes before. See, ideal cycle time of which is 1 minute. So, 60 second will be the Tc. For similar transfer lines, the breakdowns of all types normally occur with 0.1 breakdowns per cycle, and the average downtime per line stop is 6 minutes. So, this is the Td, if you remember that. Okay. So, this is the time taken for diagnosing the problem and rerun the machine. The raw material costs rupees 50 each. The cost of operating the line is rupees 2400 per hour, and the cutting tool's cost is rupees 6 per piece. Considering the scrap rate of 5%, evaluate only for good pieces, production rate, time to produce 1500 pieces per week, line efficiency and the cost per piece. So, here if we have to make the solution, first of all you have to remember that what are the things which are given here, all right. Now, let us see average production time per piece, this Tp, if you remember, that was Tc plus the breakdown effect, and breakdown effect is the Td, the time taken, and the frequency. So, here Tc is given as 1, okay, we are taking as in minute, and frequency is 0.1 breakdowns. Then the 6 given is the TD, okay. 6 given is the TD. So, therefore, 1 plus 0.1 into 6 will be 1.6 minute, which is the average production time per piece. So, once we find out that, we can find out the average production rate, which is 1 upon this time, and this will be 1 upon 1.6, which is 0.625 pieces per minute, or 37.5 pieces per hour if we multiply by 60. Production rate of good parts, because we have said that considering the scrap rate of 5%. Okay. Now, the production rate of good parts therefore, will be 0.95 because of the 5% of scrap into this 37.5 pieces per hour. So, actually what we will be getting is the 35.625 pieces per hour. These are the good pieces. Next is the time taken to produce 1500 pieces. So, per week given is immaterial, because these many pieces is planned to be made within a week. So, how much time it takes, that does mean. So, time taken to produce 1500 pieces overall is 1500 divided by, this is the production rate. So, 35.625 for the good parts only, because the 5% scrap rate we are considering. This will be 42.1 hour or 2526 minute. Therefore, the line efficiency, this will be TC divided by 1.6, 1.6 is TD. So, TC by TD, this will be the line efficiency, which is 62.5%. And finally, the cost per piece, cost per good piece, because evaluate only for good pieces. So, for cost per good pieces will be 1 upon 0.95, this is the 95%, into 50 plus 40 into 1.6 plus 6. So, if you remember the formula, it was the raw material, line operating time and the cost plus the tooling. So, here the tooling is given as the cutting tool cost is rupees 6 per piece. So, it is coming in here. Okay. 40, this is the line operating, because it is the 2400 rupees given here. So, the cost per good piece will be 126.315. This is the solution. So, here we are using the theory that we have learned in the flow line performance analysis, and you can find out the production rate, time to produce number of pieces, efficiency, cost per piece and so on. Now, suppose in the second example, it is decided that the rejected components in this problem, those which are rejected, they have to be repaired, and the repairing cost is rupees 80 per piece. Suggest whether it would be economical. Now, let us see, if we have to repair with a cost of 80 per piece, then how this problem will be changed. Now, this is gone, okay, because this is that actual cost, which is the raw material, line cost and the line and the rejection cost, and the rejection in the sense that what we are saying as the for the breakdown, okay, for the breakdown and the tooling cost. So, apart from that, we have to incur a cost of rupees 80 per piece. So, that we are giving with the good pieces. So, good pieces, therefore, 0.05 it has to be multiplied by the cost, okay, and overall these are not changing. Okay. So, 50 plus 40 into 1.6, this is the TD, plus 6 is the tooling cost, plus this cost for repairing, that is rupees 80 for good parts 0.05, and that will be 124 rupees per piece. So, this is less than 126.315 rupees. So, therefore, it will be economical. See, these are the analysis. This analysis is given particularly, this example is given particularly for you to have an idea of whether you will actually reject the parts and throw it out, what is being done in many cases, or you are going to repair. But before you repair, you have to find out, you have to analyze this way, that whether it is economical, because we are not talking about one part, we are talking about the thousands of parts which are being produced and which are being also rejected. The rejected parts are also too large a number. So, you have to find out, analyze whether it will be economical, then you decide that whether you have to repair or you will be able to throw them out. Next example I have taken on the vibratory ball feeder. Let us discuss it, whatever we have just now discussed. Let us say the problem is for a vibratory ball feeder with 3° track inclination angle. So, if you remember, we said that practically for mechanical design the track inclination angle has to be 3 to 4°. Although I remind you that at a 0° track inclination angle, the F into Vm, it is a conveying velocity, part conveying velocity is maximum, but we have to give it because it has to be inclined and it has to go spirally. Now, for a 3° track inclination angle and 30° vibration angle, determine the values of dimensionless normal track acceleration, which is An by Gn, and the amplitude of vibration A0 for a positive feed rate to occur. So, we have to find out that F into Vm, so that the part goes up the track and not backwards. So, limiting condition for forward motion is tan of the vibration angle is equal to tan theta divided by mu square. You remember that we have done that this is the forward motion, finally we got it there by simplifying. Therefore, mu square is equal to tan of the psi divided by tan of the theta. Psi is given as the 3°, this is the vibration angle, and the track inclination angle is 30°, which is the theta. So, tan 3 divided by tan 30, which will be 0.0907, and therefore, the mu will be 0.301. You can find out square root of this. Next is we found out the mu because we have to find out the dimensionless normal track acceleration, which is more than for the parts to go up the track. The condition is that the normal track acceleration has to be more than the mu plus tan theta divided by cot psi plus mu. Theta is the track inclination angle, once more, psi is the vibration angle. So, theta and psi given, mu we found out 0.301. So, you can find out the condition is An by Gn is becoming 0.174, okay, meaning more than, this is the mu plus tan theta divided by cot psi plus mu is becoming 0.174. So, An by Gn has to be more than that, so that the parts can go up the track. Now, An by Gn, now next we have to find out the amplitude of vibration. Okay. Now, An by Gn we know that this is also A0 can be defined as A0 omega square sin psi divided by g cos theta. Okay. So, from here you can find out that A0 this is equal to An by Gn into g cos theta divided by omega square and the sin phi. So, this is what we are doing. Omega is 2 pi f. So, this is the angular frequency, if you remember, angular frequency is 2 pi f, okay, and f we know that this is 50 in India, 50 hertz, okay. Pi is equal to, you know that, 3.1417. So, this is you can find out. So, we have found out that this is equal to this is the omega 314.6 and this is omega square. So, overall we can find out this is the g, overall we can find out that this is the amplitude of vibration will be 3.44 into 10 to the power minus 5 in meter, meaning that here we can actually see the direct implementation of the theory that we have seen, okay, that we have studied before. Okay. I hope this is clear, all right. Now, our next feeder, that for the small parts, that one we have discussed the vibratory ball feeder. The next feeder we will be discussing as the reciprocating tube hopper feeder. Okay. Now, in reciprocating tube hopper feeder, how it works? Here there is a feeder, there is a bowl, okay, and the mass of the parts, small parts will be inside the bowl. Now, within the bowl, through the mass of the parts, there is a hollow tube which reciprocates, goes up and down, all right. So, the reciprocation can be made by a cam device, okay, by any mechanism which will actually can reciprocate the tube, and while it is going through the mass of the parts and going above the mass of the parts, in this process, since this tube is hollow, the parts from the mass of the part in the bowl located in the bowl, they will come one by one, they will come and go inside this, and it will be coming from the bowl feeder at the exit. Now, of course, in this design you understand that they have to be sealed so that the parts do not go in this way from here. So, they have to come inside this hollow tube, all right. And as you can see that the hollow tube up here, it is actually slanted, okay. It is cut slant, because any part which will be coming on this tube, so that they cannot block, okay. So, if it is slant, so part will come and it will actually slide. So, therefore, this is slanted here, okay, and parts cannot block the entrance of the tube. Now, this kind of hopper feeders are very simple in design, as you can see, and they are very efficient, and they are used actually in the production for transporting the small parts from the feeder to the outlet. Okay, from here where it goes to the assembly machine where the parts are being assembled. So, that means the assembly machine is taking these parts from the feeder, and those feeders are different. Like for example, we have seen initially the vibratory ball feeder. There the principle is that by the vibration we are actually moving the parts. Here it is even more simple, that this reciprocating tube actually taking the parts one by one. These are this can be used for cylindrical parts, for round shape parts, okay. And accordingly the inside silhouette or the inside shape of the hollow tube should be made accordingly, according to the shape of the parts. Here there is a sealing, okay. This will not disturb the movement, reciprocating movement of the tube, but at the same time it will not it will prevent the parts to fall and block this part actually, okay. Now, while designing this hopper feeder, however, it is very important to see that the parts should not jam between the reciprocating tube here and the hopper wall, okay. That means the hopper wall, this angle should be made in such a way that this jamming does not happen. This is very important. Let us say for example, here we have the diagram, this is the side of the reciprocating tube, let us say this tube, okay, and this is the hopper wall, this is the line, this is a line diagram. So, this is the hopper wall and this is the side of the reciprocating tube. Let us say this is the part, okay. It is a cylindrical part, and the cylindrical part is jamming between the hopper wall and the side of the reciprocating tube. Let us see what happens here, and to prevent that jamming, what can be incorporated in the design of the of this kind of a hopper feeder. So, let us see in this line diagram, we have the normal force here N1, okay. We have the normal force here as the N2, which is being imparted on the part from the hopper wall, okay, because of the weight of the part itself, and this is from the side of the reciprocating tube. Now, F1, this is the force which is required to drive the tube, reciprocating tube, this is the F1. F2 is the friction force, okay. Here it is written, F1 is the force driving the tube down, and F2 is the friction force because of the normal force imparted on the part here from the hopper wall N2. N2 is the normal force, because of that the F2 which is the friction force, F1 is that force which is required to drive the reciprocating tube, okay, through the mass of the parts. Then W is the weight of the part, okay. Now, here the W is not exactly weight of a single part. Now, on this part, since it is a mass of the parts, on one part which is here as shown here, there are other parts located. So, the W is the weight of this part plus other parts which are stacked on this part. Let us say this is consolidated as W. D by 2 is the radius of the job of the part, it is d by 2 here. Phi is that angle between the side of the reciprocating tube and the hopper wall. Okay. So, then in this case let us see the equilibrium equation. So, along the N2, okay, what we will have? Sorry, let us say along the vertical distance, okay, along the vertical direction. Along the vertical direction we have the F1 in this direction, okay. We have the W in this direction straight. Then we have the F2 which is inclined. So, therefore, it has to be F2 and the cos phi. So, that means what we are telling is that let me take the pen. What we are telling is that this will be there will be two components, okay. One component is here of F2 and one component is here. So, this component we are taking as the F2 cos phi, all right, because it is we are taking the vertical forces. So, F1 W and the F2 cos phi, this will actually be this is in this direction, okay. This is in this direction. So, in the other direction will be N2 and the sin phi. This is the two components, again we can take here, one is here, one is here. This is the component which will be N2 and the sin phi, this component. So, since this component is going on the other direction, so this force and this force, they will be resisted by the N2 sin phi, that is what we are saying. So, then this equation comes as the equilibrium, that F1 plus W plus F2 cos phi is equal to N2 sin phi. Okay. So, this is the force equilibrium in the y direction, let us say, in this axis. In the N1 direction, that is the x direction, we have N1, then we have the well, I will remove this thing now. Okay, we have the N1, this one, then we have the N2, that also we can actually we have resolved into two components, one is here, one is here. So, this will be the N2 and the cos phi. So, we have N1 which is resisted by N2 cos phi, and it is also resisted by the F2 and the sin theta, sorry, sin phi. So, this is like this here and here. So, this is the one which is F2 and the sin of the phi. Okay. So, N1 in this direction is resisted by F2 sin phi and the N2 cos phi. This is clear. So, this is the in the x direction, this is in the y direction. Now, let us see that if we say that point A here, this is the point A. So, about that point all the moments that are being produced, this will be, let us say F1 is carried over up to this. So, this will be F1 into d by 2 plus from here it has to go here because about the A axis A point. So, plus F1 cos phi into d by 2. So, that is what we are writing here, F1 d by 2, it comes from here to here, plus F1 d by 2 and the cos of the phi. So, because it is inclined, this is okay, plus W will be vertically. So, if it is to be coming here, so it will be W into d by 2 and cos phi. This will be resisted, they will be, this moment will be in this direction, in the clockwise direction, okay, because F1 is giving that moment, W is giving that moment. This will be resisted by something which will be coming anti-clockwise, and the anti-clockwise it is coming as a N1. N1 will be coming to this point and then to this point. So, this will be from here to here, it will be N1 into d by 2 into the sin of the phi. Okay. So, this is another equation which is the moments, all moments around the point A. Now, we have these three equations. Okay. Here phi is the hopper wall angle once again, and d is the diameter. So, d by 2 is the radius. Now, we will take from this equation the value of the w, okay, value of w, and put it in equation. Let us say this is equation 1, okay, or rather 4.1 we have said. So, let us say this is 4.1, this is equation 4.2, and this is equation 4.3. Okay. So, from 4.3 we will take the value of w and we will put that equation and put that value in here. Here we have the w. Okay. So, after rearrangement what we will be getting is this. Let me show it to you how it is getting. So, we have the equation 1 here, 4.1 here, okay, 4.1 here, and from here we will find out the w is equal to this. We have the equation 4.3 here. So, we take the value of, sorry, we have to, earlier what we said is a little different, like w value we will be taking from the equation 4.1 and that value we will be putting in the equation of 4.3. Okay. So, 4.3 is this equation, this is actually 4.3 and this is 4.1. So, we will take the value of w from here, we will put the value here in this equation. So, it will be like this, because w is becoming n2 sin phi minus f2 cos phi minus f1. This exactly this value we are putting it here in place of w. Okay. So, remaining will be cos phi here, all right, and the d by 2 here, and the remaining is the same. So, if we solve this equation, it will be in this form, n1 sin phi we are taking it from here, okay, d by 2 we are cancelling from here in all this. So, we are taking n1 sin phi is equal to f1 this and this remaining. Now, f2 this is equal to n2 into mu s. Let us see this. What we are saying is that F2 is the friction force because of the N2, which is the normal force. So, therefore, F2 is equal to N2 into mu s. So, we are putting that value of F2 as the N2 into mu s, we are getting this, and simplifying we are getting this equation. So, that finally, we are getting that N1 sin phi is equal to F1 into 1 plus cos phi plus cos phi into this factor. Okay. So, how this is getting affected, and from these three equations how you are getting into the design aspect, that I will discuss in the next class. Thank you very much.